Okay, give me 1 second. I'm contacting the speaker.
Hello.
Hi, how?
Sorry, I was trying to find the link.
Oh, yeah.
Okay. When do we start? Now?
Yeah. Thank you for joining.
Hi.
I think, yeah, we can start now. Yeah.
Do you want to try sharing your slides first?
Yes. Give me 1 second. I'm just trying to find the slides.
Thank you for joining. I know it's evening, or is it evening or afternoon where you are?
Oh, it's actually afternoon, 5 p.m. Okay. Let me find the slides. All right, there you go. Can you see it? Actually, let me try full screen and then we can see if it works.
I guess we might also have like lots of the videos, so it might be good to try to play some of them.
Does that work?
Yeah, the full screen works.
Oh, I'm actually in the second slide already. Is it not working?
We are seeing the title slide.
Ah, okay. So I think, you know what, let me let me try to share not in full screen.
Okay.
But there's a way to actually just share part of it. Advanced sharing option, share screen, advanced portion of the screen, share. Okay, so let me try that. Okay, now it should work, right? So this is first one, second one. I can press it and then it plays something.
Yeah, it works.
Okay, good.
Yeah, cool. So yeah,
right.
let me briefly introduce you first, and then maybe let me share my screen first, and then maybe you can switch this slide. Okay. Okay, cool. Can everyone see my slide and hear my voice?
Yes.
Okay, yeah, thanks. Okay, good morning, everyone. Welcome back to Colloquium talk at KAIST School of Computing. Today, we are going to have the last talk of this colloquium this semester with a very special guest, Hao Li. Hao Li is a CEO and also co-founder of the Pinscreen, which is a startup building the cutting-edge, the AI-driven, the virtual, the avatar technologies. And he's also a distinguished fellow of the computer vision group at the UC Berkeley. And before that, he was also a associate professor of the computer science at the University of Southern California, as well as the director of the vision and the graphics lab at the USC Institute for the Creative Technologies. And he was also previously a visiting professor at the Weta Digital, and also a research lead at the Industrial Light at the Magic, the Lucasfilm, and the postdoctoral fellow at the Columbia and also the Princeton universities. And he was also named the top 35 innovator under 35 by the MIT Technology Review in 2013, and also the DARPA, the ISAT, the study group in 2019. And he also won many awards, including the Office of the Naval Research Young Investigator Award in the 2018, and also Google Faculty Award, the Okawa Foundation Research the Grant, and the Andrew Ona Bitterby, the Career Chair, and also the ACMC grabbed the Real-Time Live, the Best in Show Award in 2020. And how also work in the computer graphics and the computer vision focuses on the digitizing the humans and capturing the performances for the immersive the communication, the telepresence in the virtual worlds, and also the entertainment. And he also did lots of the seminar work in the avatar creation, facial animation, the hair digitization, and also dynamic shape processing, and also his recent work in the preventing the spread of the malicious the deepfakes. So thank you, Hao, for the giving the talk today, and also for everyone. Please join me in welcoming Hao, and Hao will talk about the AI synthesis from the avatars to the 3D scenes.
Yeah, thank you. Thank you, Minhyuk, for the introduction, and also thanks for having me here speak at KAIST. It's a great honor. Great. So let me share my. Am I sharing right now?
Not yet.
Oh, okay. Sorry.
Okay. So let me also start recording.
Yes.
Okay.
Okay. So let me share my screen.
Yeah.
So today's topic is on AI synthesis from avatars to 3D scenes. So it will highlight sort of like the recent work that we're actually doing in the space of how do we use recent deep learning advances to generate content and also to digitize content. And before I start, I'd like to talk a little bit about the motivation of what we're trying to accomplish. So ultimately, what we're trying to do is basically create virtual worlds. And this is a hot topic these days because everyone cares a lot about the metaverse. How do we think about next generation content for augmented and virtual reality? The idea is that we can sort of like go beyond 2D video streaming, and how can we enable things such as immersive telepresence? And a lot of big tech companies like Microsoft or Meta are working on these kind of new capabilities. And at the center of it are digital humans, right? So it's really trying to digitize ourselves and enabling things, allowing us to interact with each other remotely and also immersively. And if we go back, 6-7 years, one of the things that we saw was, some of the early pitches from Facebook on how they see the future of, building a more open and connected world beyond what we see these days as the web interface. And we actually worked with them very early on. So that was back in 2014 where we started our collaboration. And if I remember correctly, that was one of the first paper with Oculus. And what we built back then was a system allowing people to not only digitize themselves, but also having a way for them to capture their performances and map those into a virtual environment. So this is this really bulky headset prototype that attaches like a depth sensor to the face so that we can capture what the mouth is doing. And it also used like some internal sensors on the phone pad so that we can sort of like track what the facial expression is doing. So the purpose there was really just to prototype a system together so that we can see how interacting or talking with each other in virtual reality would look like. 1 year later, we started to work on something slightly more sophisticated. So we worked on a purely optical system. So it's a VR headset from a company called Fove. It had internal IR cameras. It was one of the first back then that had that. And we also built like a smaller camera. So basically a PlayStation webcam that is tiny enough and then could be attached actually to the headset. And what was actually new here is on the software side, which is a solution allowing us to map input data that was where it's difficult to track features, right? So the approach that we took is basically to use a deep learning approach. It was one of the early papers that we work on that used actually a deep neural network to basically improve the mapping from data that is difficult to track. And so one thing that we could show is that we could reliably get facial expressions into a system so that we have the ability to control our avatars. Now, if you fast forward a couple of years and see what's Facebook and now Meta has been working on, are these very sophisticated photorealistic renderings and also digitizations of humans, and allowing people to interact with a very appealing avatar of themselves. This is a work from Facebook Reality Labs that they presented called Avatar Codec. And the idea here is that they would use a multi-view video system, capture the appearance of the person from multiple views, and record all kinds of facial expressions. And then at runtime, they would use partial views in order to infer the entire head of the avatar and stream that in real time. So it's a big system that has some very fancy features. If you, in case you missed the recent keynote from Mark Zuckerberg, you can see that they were showing some really interesting stuff where they digitize an entire person, most likely using a combination of body tracking as well as neural rendering. So they capture a person probably from multiple views, and then they showcase that it's possible to stream this hybrid CG and neural rendering of the avatar from one place to another, right? So this is really for enabling a more convincing system for telepresence. Now, the motivation for building realistic avatars is not only for enhancing communication between us, but it's also for enhancing communication between us and machines, right? So human-machine interactions are likely to replace many of the existing services that we have on a wide range of domains. So it's customer service, or when you order food in a restaurant, or if you want to buy tickets, most likely you'll have something more intelligent in the near future, right? And there's some really interesting work, like the work from Soul Machine, where they're building these virtual avatars. And also Samsung actually presented recently, or 1 or 2 years ago, with Project Neon, a photorealistic avatar where people can have the ability to interact with them, right? So people are trying to explore how can we make interactions either between humans or between humans and machines more natural. And the most natural interaction is between another human. And another space where it's really interesting is when we talk about things like live events or just simply content, right? So as we know that there's a lot of global events that are being less desirable to go to, people are also exploring things like virtual concerts. How can we sort of scale these kind of experiences to something that you can't actually do in physical life, right? So how can you, for example, have a virtual music concert where you have millions of people attending, rather than just a few thousand in in a physical space. And it's more than that, right? It's also, how do we even use humans to engage with fans, also to do marketing? So there's a strong interest these days, especially with how people are trying to re-architect what the next generation of the internet is going to look like. There's going to be an increasing desire to virtualize a lot of things, and also to create a spatial experience. Many of the social media companies like Snapchat are also looking into bringing, augmented reality things beyond, the way we consume them nowadays with cell phones. But how can we fully leverage three-dimensional content, and how can we actually bring those kind of experiences to a mainstream audience? So in the near future, we're going to experience a lot of these virtual and immersive experiences for mainly three directions, right? One is communications. We want to enhance our communications between us. We want to enhance our communication between humans and machines. And most importantly, content creation is another area where immersive content is going to play an important role. Now, at the center of this are digital humans, because we're actually creating these things for ourselves. And we all know that the creation of digital humans is something that's non-trivial. We've already seen that digital humans in visual effects, for instance, is something where we can already see extremely high quality digitizations of them, but then the generation of them requires a huge production effort, right? It's something where you need hundreds of digital artists. It's something that requires a long rendering time, and also the asset creation is something very, very complex. So in order to enable applications that we have demonstrated before, something that brings these kind of technologies from production studios, but to the hands of people, we need to focus on two important aspects. One of them is it has to be interactive, so it has to be real time. And the second thing is we need people to be able to digitize them. It has to be as simple as how we capture content these days with a cell phone. So let's talk about the first one. So on the real-time aspect, there has been a lot of advancements in the past few years, especially on the digital human side for real-time graphics, right? So this is a demonstration of MetaHumans from Epic Games. So MetaHumans Creator allows you to create highly sophisticated, very realistic digital humans and run them inside an Unreal Engine. And I think these days you'll probably, like maybe today or tomorrow, you'll probably see some big announcement where you can even see like a photorealistic Keanu Reeves for a new demo from the Matrix using some tech behind MetaHumans. But it really showcases where the future is going, right? So an interactive experience allowing you with very realistic humans. So the other problem is, how do you create that content, right? So even though you need an authoring tool or some sophisticated scanning capabilities, these things are still for production studios. Also, in order to run this kind of quality, you still need a very powerful device. But regardless of powerful devices, if you want to digitize a person, the best way to digitize them still is to capture the best possible data from that person. But obviously, if you look at some of the work we've done in the past, back at, for example, USC ICT, is that for production use, we still prefer to deliver the best possible asset we can capture from a person using the best possible capture device. So for example, you put a person inside a device like the light stage, or you can use a multi-view stereo system, and they would get high quality data. But the problem with these high quality data is, first, you need to pre-process them. So you need to create very clean and high resolution data that matches the scan that you have captured. And it's not just the geometry, it's things like texture. You need to create custom shaders that have the ability to perfectly represent the person that you have digitized inside a new virtual environment, right? So ultimately, after you scan that person, you need to be able to re-render them in a new CG scene. And this, unfortunately, is something that still requires many, many different steps, right? So you create the models, you rig the person, you clean up textures, you have to create dedicated shaders that work in certain environments, and you have to integrate that with the body and everything else. And everything has to sit perfectly right in order to get the best possible quality. Now, the pre-production is a huge effort. And then the second thing is the capture process is very tedious. So you need a system like this. Now, in the future, you can't, it's impossible that people are going to all have like a device like this at home and have a production studio to help them build their avatars. This only makes sense for production. So to democratize this kind of process, one of the goals that we had at Pinscreen is basically to say, how can we make the creation of realistic avatars as simple as, let's say, taking a photograph of a person, right? So it has to be as simple as this. And obviously, one of the issues here is in order to digitize a high quality avatar from a random photograph, you have to be able to deal with unconstrained images. And these unconstrained settings have properties like maybe the person isn't even in a neutral face. Maybe the face isn't, front facing. Maybe it's something that you've downloaded from the internet. And one of the issues that we see the most often are the lighting is bad, or the person hairstyle is actually occluding some of the face, right? So maybe you have like a hair strand that's like, or part of the hair that's actually occluding half of the face. And you don't want to build something that, ask people to go through a proper capture process, right? So it has to be something that works in the wild. So the approach that we have, and we have at Pinscreen, we have developed multiple systems over the years, right? So some of the early systems that we developed are based on, morphable face models, which is basically you have a linear model that is describing the identity of the person, or you have a linear model that's, representing facial expressions. And then what you do is you try to fit that model to the photo, and then you try to neutralize the person's face. Now, this works to some extent. And as far as I know, most of the avatar digitization techniques that are out there all are mostly based on this technique, right? So you can see that there are multiple methods that have been developed, and some adds different components in order to make this more robust, faster to compute, or in a way that can handle better details, right? So the idea is the most basic approach is that you have a linear face model. You use a method like gradient descent in order to optimize. So you pose a energy minimization problem. What you say is that, well, what is the best combination so that it fits the input photo as good as possible? You try to detect some features and you try to minimize distances. Or you would minimize texture appearances and try to solve for the best possible combination so that the model that you're digitizing matches the input photo. Now, with all kinds of gradient descent methods, we know that they always depend on your initial value. So what it means is that very often you have the problem that you can get stuck in some local minima. So your optimization can have a problem. And the other problem is that if your model is like a purely linear model, then the space of variations becomes trickier because you're kind of limited by this dimension reduction, right? And for example, if you have in your database that you use to train your linear morphable face model, you have people with beards and some without them, then a linear blend between them would be someone that has sort of like a lighter, beard. So a lot of these non-linear variations are more difficult to represent using a linear model, right? So first, people came up with how can we use, or started to adopt deep neural networks to improve the robustness. So instead of starting off from or trying to have a better heuristic to start off from some values and start to optimize for your face model, what people would do is they would try to train a deep neural network that would infer directly for a better value or infer for the final result directly. So that's one way of optimizing it. And most recently, there's actually a work from Lee et al. Where they actually use a combination of deep neural networks for inference, but also a nonlinear 3D MM model in order to get high quality face variations for the data. The only problem is that here you do have lighting and facial expressions that are baked in. And if you want to neutralize them, it's not always easy, right? So it's hard to guess what the person's face actually is. So it's an ambiguous problem. So we started to look into that problem a couple of years ago, and we started to think about, why don't we just take the input photo and normalize that input photo? And so the group at MIT and Google started to look into a work where they used a encoder-decoder strategy. So they take a photo and start to extract the likeness, the identity of the person, and then generate a normalized photo of that person in order to get the neutral face. So this works to some extent. The resolution, the initial method that they had, the resolution was relatively low. But then the problem is that you lose a lot of details because the underlying model is still linear, right? And even if you have that, it doesn't guarantee you that the 3D model in the end has, can be optimized to fit that person. So that's the issue. So even if you get a perfectly frontal face, having a 3D model that really represents the person still requires you to fit to that person. So that 3D modeling process also needs to be good. Now, what we came up with is an approach that at least generates higher resolution details. So instead of doing this in a single pass, what we did is we split this problem into multiple ones. We first undistorted the perspective distortion from the camera. So we have a normalization step for perspective distortion. And the second step is basically one that normalizes lighting. And then the third one is normalizing facial expressions and poses. So this works if you have enough data, but fails in places when the head is turning too far apart or when the lighting is still too extreme. So it's very difficult to actually handle all kinds of situations and also to train all these separate networks. So our method was not train end-to-end, which is a little bit more challenging. And if you have one part that doesn't work, it would basically propagate to all of them. So you'll have an issue there. So we started to think about, can we somehow do something that is a bit like the first work, but generates the 3D content directly, but at the same time normalizes the facial expression? So this problem becomes harder because for 2D images, it's fine because there is so much 2D data. So how they did it is basically they took a random photo, use a face recognition network to extract identity features that matches the person, and then they would basically generate a frontal face. So face recognition networks are well trained because there's so much 2D images out there, and you can use something like FaceNet, but and there's a bunch of other face recognition networks. But then the problem is if you want to do this in 3D, it becomes much harder because there isn't so much 3D data for training. So that becomes one of our issues. So let me show you what we came up with. So we came up with this approach that was published at CVPR this year. So the solution is to do a normalized 3D avatar synthesis. So the idea is that you give them like really crazy input. I mean, it doesn't have to be crazy, but if you're given these input images, we can actually generate a neutral face in 3D of that person, right? So if you have every person in the world, or let's say if you have like a few 100,000 people in the world, and for each of them, you have their ground truth 3D model, then you can use supervised learning in order to build that. But instead of using, but the problem is you can't expect someone to have that much data, especially with a lot of variations. So the idea here is to, first of all, think about how can we actually generate sufficient training data so that we can even train a network so it doesn't overfit. That's one problem. And then the second one is how can we still manage generating a person that has the likeness of the input person, right? So there are multiple things here. So, and also if we look at the challenge that we need to handle, so this actually shows it's pretty crazy, right? So what if you have like, so we really want to be able to handle that. So a person that does like really crazy facial expression as input, someone with like really bad lighting conditions, or even like, you know, this is like a colored lighting. We know that if we look at that face, it's not a painting on the face. It's not a Braveheart painting, but it's really a light that's there. But if a person is not even looking at the camera, but really like facing sideways, can we still extract it? Or if a subject is wearing glasses, right? So glasses are another problem that could be an issue. So first of all, what we do is we split this problem also into two parts. The first part is we infer a 3D model directly. So to infer a 3D model directly, what we do is we use an encoder-decoder structure that says from that input photo, extract the likeness and generate for me a textured 3D model of that person directly. And the idea here is that we use a very powerful decoder. So we use something that's based on StyleGAN2 that has the ability to actually digitize that person. And the idea of like creating a 3D model, textured 3D model is, I mean, for the texture is, it's easy because it's a 2D image. So StyleGAN generates 2D images. But for the 3D model, what we do is we basically stack XYZ coordinates for each pixel. So what we have here is actually a positional map that represents that actually 3D mesh. So when you combine both, you actually get a 3D model. So this gives us a pretty good initial value. And afterwards, what we do is we try to improve the likeness by transferring the final likeness from the input image onto that model, right? So the first stage is actually super fast. It takes less than a second. And then the next one takes multiple seconds. So it depends on how many iterations we want to do. But the second stage basically does a differentiable rendering approach in order to take that input model, fit it to the input image, and then backpropagate gradients in order to compute the difference so that we can apply the offset on both the geometry and the texture to improve that face. So let me explain that a bit in detail. So what you see here is that you have the input photo and you have something called FaceNet, which basically is a face recognition network that extracts the likeness of the person. We bridge this to StyleGAN using an identity regressor network and train this whole thing end to end. Then for the refinement stage, we use a differentiable rendering approach. So the idea is that we start off with the StyleGAN latent vector, use the StyleGAN to actually generate a positional map with the albedo texture. So that's basically the previous step. So we generate that. And then what we do is we use separate networks, one PSP-net basically to extract the face region. And we use the rest net to basically regress to camera parameters or head positions, right? And once you have these, actually you need both. And once you have that, what we do is we use a differentiable renderer to compute the difference. But instead of minimizing pixel values, we don't want to minimize pixel values because otherwise you will transfer. So for example, otherwise you would transfer the blue lighting here from that woman. So what you do need is you need to, we basically use a perceptual loss to minimize the distance. So then the person still looks like the person, but uses the texture that was inferred from this normalization inference step in the beginning. So I can show you a quick video and I can show you a live demo later. So this video, you can actually see one of our engineers, Sergeant. So he's taking a photo of himself and you can see he's actually smiling in that little corner here. And it basically generates like a complete avatar, right, of himself. So this is a, bigger system that generates, the head, rigs it together with a body, and then you can use that inside your video game, right? So that's something that we're incorporating these days with multiple clients at Pinscreen. So here you can see a couple of results. So you can see even with black and white images, we can generate a reasonable skin tone for the avatar. This visualization shows how we can actually render them properly inside new lighting conditions. And you can see, right? So with various subjects, it gets like the likeness quite right. In this example, this is what we do actually to check the how consistent the result works for the same identity, but with pictures that are taken from different angles, different points in time, and also with and without glasses. It's not perfectly the same, but it's relatively close. We also try to test it on a video input. So every frame is processed separately. So these were results from a couple of months ago. But you can still see, right? So it's not, I mean, it's impossible to get exactly the same values, but it's pretty good, right? And this person was not in the test, in the training data set. Here's another example, right? So what happens if you put extreme lighting conditions that have colors onto a person's face? You can see that the skin texture is actually well inferred from actually mostly the likeness of the person. So because we trained appearance and geometry together, it has the ability to get a good prediction about what the skin tone is. So this is sort of like to give an idea of how our avatars look like. I can give a quick live demo. Let me see if I can share my screen. Here I can try to share my screen. Let's see if it works. So this is like an avatar generated previously. So let me first use, let me press the button here to recompute. So that's not using the cached version. Let's try out a few so we can find some interesting avatars. Let's pick this guy, our favorite actor from Squid Game. So the way the system works is that you take a photo. So this is actually downloaded from the internet. And here I just upload, I can select the person I want to upload, and it sends the picture to our server, and which is computing it. The thing that takes the most time right now, it's actually the perceptual refinement step, which is the thing that's based on differentiable rendering. And then it's generating it. And then once it's done, it loads it back into the system. Yeah, let's wait a little bit. Yeah, so yeah, here you can see. So you can see that this is sort of like the face that it generated from that photo. And it's funny because it actually removed the blood that's on his face, which is kind of due to the fact that in the training data set, most people, we probably don't have anyone with that has actually blood. So here, face is entirely generated automatically. The body is generic, but the skin tone of the body is actually inferred together with the face. And so I can make him move, and he can also have some facial expressions on his face. So it's a fully rigged model. Right. Okay, so I can do more things later. Let me move on with the lecture. Okay. And so this implementation is actually a Unity implementation. We're actually building a next generation implementation for Unreal that has more sophisticated shading and better hair rendering as well. So this is sort of like a in progress work to show a little bit how it looks like. We're also creating a new system that not just digitizes faces, but also has the ability to digitize body shapes. So what's important here on the right, this is not created from, it's not modeled by an artist, but it was specified by, height, weight, and, waist size and these kind of parameters. So basically a high quality SMPL model that isn't, has like proper textures that, and also dynamic textures that can actually, and also a high quality rig. So it has correctives and all these things that you have in production pipelines. Also, we're building new tech that allows us to customize people, customize clothing to people with arbitrary body shapes. So clothing is actually not easy. People normally would basically use a simulator to simulate onto people. But when you have new body shapes, then you need to fit them automatically. So these are some of the things that we're looking into. All right, so now I talked a little bit about how to create parametric models of avatars. I'm going to show you a little bit like some of the stuff that we've done to make them move, to bring them to life. So maybe some of you have seen some of the work that we've done in the past couple of years, which is how do we use GANs, not just to generate an avatar, but also to create expressions from them, right? So some of our early work uses a photo, and you have a driver, and you can condition that using an image translation network, and you can generate some faces. You can further push that and build more, build a model that not just uses a single photo, but uses, a video as training, so multiple frames. You can build more convincing faces and do things like real-time deepfakes, right? So this is not the standard deepfake pipeline. This is, first of all, it's a real-time system, but it uses our a framework that's based on our SIGGRAPH Asia paper from 2019, I believe, where called Pagan, where you're basically tracking the face to map the expression of the person. Also, what's nice is that you don't have to train per new user, so you can have any person go in. So that was something that we demonstrated at the World Economic Forum a couple of years ago, actually last 2020, where we basically wanted to show how you can do actually face swapping in real time. But
sorry,
we're not.
We are not seeing the slides in the full screen now. Sorry.
Oh, you're seeing what? Oh,
we are, yeah.
So okay. So when did you stop seeing my share?
After playing the some videos, I think. Yeah.
Oh, okay. Yeah, I should use the portion of the screen. Okay, so now.
Yeah.
So did you guys see this?
Yeah, we are seeing the high-end. Now we are seeing the videos. Yeah, in full screen.
This you have seen before.
Yeah.
And this one as well?
Yes.
This one as well? Okay. Okay, so you didn't see the video. You just saw like a static thing.
Well, we watched the video, but it was not just in the full screen.
Okay, sorry. But our goal is not to build deepfakes. So we're actually building a solution that allows us to also generate very realistic facial expressions for avatars. And one of the idea here is to, instead of swapping one face of a person with the other, you basically use the neural rendering approach to increase the fidelity of CG avatars, right? So in this example, you can actually see how we turn a Unreal rendering of a face into a realistic person using just a couple of minutes of video recording, right? So you train it, you train the model that allows you to map from the CG one to the 3D rendering. And what's important here is that this is a solution that actually integrates straight into the game engine, so that we can actually use parameters from the game engine. For example, the exact position of the face, or if you have something that would be occluding the face, those kind of things are provided by the game engine. So we have already started to use this technology for avatars. So it's not just some demos. We have worked with a company called Zozo to actually create virtual influencers for basically replacing fashion models with virtual ones. And one of the things that they're doing is they're sort of creating these TikTok videos at scale. So you have a wide range of animated characters that actually look pretty decent and can be rendered in real time. All right, so all these methods that I've shown so far are either parametric models or parametric models that are combined with some neural rendering. At the same time, we're also looking at how do we use volumetric, how do we, a different way of enabling telepresence is not to build an avatar of yourself, but to basically stream how you look like directly into the scene. And that's the kind of technique that is, very often referred to as volumetric capture, or in our case, volumetric teleportation. So you can kind of see this in this concept video from Microsoft. You can see, so these people that kind of look real, these are volumetric captures, and these Lego avatars are kind of like parametric models. So here they kind of combine both things. But the nice thing about these live streaming people is that, or these volumetric captures, is that they literally look like how they are, right? But the problem is, in order to capture that content, traditionally, you need a studio with a wide range of cameras that are capturing the person from all kinds of views. And just similarly to the light stage example that I was showing in the beginning, this is not something that is practical, because, unless this is for a studio or lab setting, for consumers, it's unlikely that you'll have people having a room that's dedicated with cameras, but you most likely will have something where you have either very few cameras or ideally just a single camera, right? And here's another example from a company called Evercoast. They were showing this, when you combine multiple Intel RealSense cameras, you can capture these people. But again, it's not something that would work easily. So a couple of years ago, we started to look into, well, what if you only had a single camera? Can you still digitize an entire 3D person? Can we sort of leverage like 3D deep learning on that? And in this collaboration with, when I was back at USC with Waseda and UC Berkeley, we developed this technique that is called PIFU, which stands for pixel aligned implicit functions. And what it does is that it takes an input photo, so you remove the background, and from this segmented input image, you can actually generate directly a complete 3D model, including the texture. And what's cool is that you also get the texture from views that are actually not seen in that photo. So even the back of it, it has a good way of like predicting what it should be. And there were two ideas in there. The first idea is, first of all, what we observed was, well, you could use voxels to represent your three-dimensional scene and train a deep neural network to infer your object, because voxels are basically just a direct extension to pixels for images. So you can do convolutions. But then the problem is it takes a lot of memory, and you're kind of like bounded by the resolution of how much memory you have to represent this three-dimensional space. So instead of using voxels, we propose to use implicit surfaces, which does not require you to use all the voxels for memory. And the second thing that we introduced was this pixel aligned representation. So instead of having like your full input image frame that maps to a feature vector, so even though in theory this would work, you would actually lose a lot of information, because the appearance variation of full human bodies is extremely large, right? And people wear different shirts, different pants, different dresses. So it becomes very hard to compress everything into a single feature vector. So the idea is basically to use a fully convolutional image representation, where the internal representation consists of image resolutions that matches the input image, and still have, or at least a bigger image resolution, and where each XY position, you do have like a feature vector that describes, that relates the entire image with that specific point. So by combining these two ideas, we get these back then really impressive 3D models of people. So here you can see, right? So from these photos, you can get the full 3D model of that person. And even though that person is holding something, right? Even that person is holding this dress, it has the ability to capture it, but you can see it kind of looks like a foot somehow. So maybe it's because of the training data, but still it generates something plausible, especially on the back of the body. You can see it generates a plausible texture for the back of the person. What's also very surprising is that it doesn't require that much training data. I think there were only a few hundreds of subjects for the photogrammetry scan, but it's still able to actually generalize to other subjects. The main problem with this work back then is that, I mean, even though the resolution is lower, and one of my previous PhD students have developed a more advanced version with higher resolution details, one of the problems is that it takes a minute to generate a single model like this from a photo. So you can't really use that for any interactive application, especially those that we talked about in the very beginning. So what we came up with is an approach that uses an octree for acceleration combined with some scheduling algorithms for multi-GPU implementation. And we demonstrated that from a single Logitech camera, you can actually digitize the entire person in 3D. And you can even get like the back of that person in 3D. So here in this visualization, you can see it's actually rotating the person 360. And while he's performing, you can actually see, things are moving. And to show a full end-to-end system, we have our subject who is moving here. We are digitizing his entire body in 3D, and we can stream that directly onto a iPad, right? So you have basically an AR-enabled iPad where you can actually move around and see that person. So this isn't exactly like what you see in things like Blade Runner, where you have like your super high quality, virtual assistant that you can talk to, but it's sort of like one step closer to that. And I think one of the things that we still don't have here is the hologram technology, right? So right now we still have to wear glasses, but there's some interesting work in the field of science where, for example, this group at Brigham Young University is demonstrating how potentially we could build holograms based on laser projections and particle systems, right? So I think this is a Nature paper, but it shows some promising direction. So it's not a completely dead idea where I think it's completely impossible. But in the future, I think people are going to see a more mainstream use using, at least in the near future, still going to be like AR and VR devices. Now let's talk a little bit about 3D scenes and not just human bodies. So for 3D scenes, we've recently done some interesting work with nerves. So everyone goes crazy about nerves in the computer vision community. And one of the main bottlenecks of nerves is that they aren't real time, right? So they take a while to actually digitize, and it's because you have to sample your space. So the work that we introduced for ICCV is this idea of using a planoctree. So the idea is that, so let me just talk a little bit about nerves. So nerves, you basically have input images, you train your nerve, your deep neural network that has the ability to render new views of your scene or object from arbitrary views. And the idea is super simple and very, very effective, which is you basically provide XYZ positions and viewing angles. And what the neural network does is that it maps this to a RGB combined with the density of that specific location and space. And when you render your object, you simply shoot array and aggregate basically all the colors combined with the density. And you can basically generate a three-dimensional volumetric three-dimensional scene from arbitrary views using this volumetric representation. So to accelerate this, the first idea is to use an octree, right? So instead of sampling everywhere in space, what you would do is you would use a spatial data structure to compress your scene. So you build this depending on your scene. And to still retain that view-dependent effect, we would use spherical harmonics that are associated with each of these cells in order to use that as an aggregation. So we basically showed that this is possible. And what's pretty cool is that you can actually, so this is a visualization of how the data structure looks like from different views. And what's really amazing is that you can have this like, multiple magnitudes higher rendering speed. So it's, it's like 1,000 times faster. And the quality seems, very, very similar. So there isn't much artifacts from that. And, you can control things like complex lightings in real time. So you can see like a nice bleeding of colors of the lights onto your scene. You can mix your scene with CG content. And the best part of it, you don't even need a GPU for rendering. I mean, you can use one, but if you don't have one, you can just use your web browser and your CPU to compute it. Why do I think that planoctrees or nerves are big? Is because, I mean, for objects, you might think that, it looks like a 3D mesh and okay, it compresses a bit better. But I think the big potential is to render entire scenes. If you think about it, when we look at AR, VR headsets, right? So let's talk about VR headsets. So for VR headsets, if you want to get 6 degrees of freedom, the only solution right now, at least to consumers, is you have your 3D game engine that has all the scenes. And if you remember, for a while when VR had its hype, everyone was talking about 360 cameras that can capture things. But the 360 cameras, you're bounded by 3 degrees of freedom, which is the only rotation. So the only thing you see, just like Google Earth, is your environment, but you can't really move around the environment. But the potential here is that you have 6 degrees of freedom for an arbitrary scene that even allows you to capture that scene very easily, right? So that's something where I think is very promising, especially for objects. You can actually move objects around, or you can be in a scene and move around. The only problem now is how do you extend to larger scene environments and how do you move around that? So there still needs to be some research around that. But I think, to me, this is like, one of the big potentials. So actually, here's a URL where you can actually download. It's actually open source, and you can play around with the code. So this is pretty fun. In the meantime, we're basically going to see mainstream AR that is still looking, I think in the near future, I mean, a lot of that work that I was showing is talking about how do we use AI to digitize things, how we use AI to render things, how do we use AI to represent entire scenes, for example, nerves. But then I think first, we're still going to see AI to digitize objects, a bit like these avatar demos that I was showing to you, because people are still using traditional game engines to view three-dimensional content. But ultimately, I think people are going to adopt more of these technologies over the years for building applications for telepresence, but most importantly for the metaverse. And to conclude my talk, so some of the big projects that we've been working on at Pinscreen, I can show. One of them is actually with Expo 2020, which is this year in Dubai. So we basically developed new technologies for generating stylized avatars. And it's not using our latest avatar, photoreal avatar, but it's building a sort of like stylized world. So you can be that avatar and have the ability to sort of like teleport yourself into the venue. So it's sort of like an app that you can download, and it's a digital twin app. So it created like a large scale copy of what the physical world is. And very soon, we're also going to launch something that allows people in the physical space to connect with those that are on their app and digitally. So the idea is really, how do we bridge that physical space and a digital one? And even though today we're still limited by graphics compute, I think in the future we're going to see some really exciting developments around this topic, especially when these capabilities are going to increase and we're going to have much better graphics. So with that, I would like to thank you all for listening, and I'm happy to take questions. Thank you.
Okay, thank you very much for the great talk about all the virtual avatars and the virtual scenes. For the audience, if you have any questions, please feel free to post the questions in the Zoom chat, or just to turn on your mic and just speak up. Yeah, so while we are waiting for some of the questions from the audience, maybe I can just start with some kind of the high level sort of the questions. So actually, I think that's really quite impressive to see some, super realistic kind of some human avatars with some kind of the recent kind of techniques. And I thought that actually there were like this kind of some sort of the virtual characters, like even for the like 10 or the 20 years ago. I think there was also kind of some virtual cell kind of things in like the 20 years ago. But at that time, the quality is really kind of the low. But now I think like we are really seeing some very photorealistic kind of this kind of the virtual avatars. So I think it was kind of the case that like for the last kind of 20 years, we are kind of like at the sort of in the uncanny valley kind of stage. Like the technology was kind of like making some sort of the human-like kind of the things, but it was not that kind of like real kind of human-like kind of things. But now we are seeing some more like photorealistic kind of things. So how do you basically foresee the future technology? Like, do you see that we are kind of like escaping the level of the uncanny valley and like just really making some real like kind of things? Or do you think that still we need some more time to make some very kind of realist kind of things? Or?
Yeah, I think there's a bunch of things to consider. First of all, it's clear that it's possible to create avatars that don't have the uncanny. I mean, avatars in movies don't really have. I mean, sometimes you can't even tell if it's real or not, right? And the main problem is that you need to put a lot of artist effort to tweak everything and make sure it looks perfectly. The bigger question is, how do we make it without a human in there to tweak that? How do we use an AI or whatever, AI or algorithm or something, like how do we computationally solve that without a human? And well, why I say AI, I think because a deep learning approach for multiple parts of it could solve it, because you can use a data-driven approach to solve that. That's one thing. Making it past the uncanny valley is one thing, and I think people are getting very, very close. If you look at the work from Epic Games, like with MetaHumans, I think I mean, it looks amazing, but then you can still tell this is a video game. But on the other hand, to be fair, if you look at what they had 5 years ago, you were also, this looks amazing, but now you're like, oh wow, what they have now looks so much better. And then I expect that, in a couple of years, it would just look even, it would always get better. But it's not just the realism. I think there's also the likeness of a person that is important, because the likeness of a person is something that is hard to describe what it is. And that's where I think the kind of deep learning approach work is much more important, because you can't have, I mean, maybe you can, but I think it's very difficult to come up with an algorithm or a data representation or an algorithm that says these features just perfectly encode that person. I think you really need this implicit approach with a lot of data to learn what is the likeness of the person. So the likeness of the person is really hard. But once you have that, people always want more features, right? They want to know, can I make that person older, younger, better looking, makeups, and there's always like more things you can do with it. But in the end, we still haven't really, it's a bigger issue, right? So we haven't completely solved how to get the perfect human there, but it's something that is ongoing. So I think this is sort of like one of the things that makes this really exciting. Yeah.
Yeah, actually, speaking to the kind of the sort of the right needs of the person, actually, while I was kind of listening to your talk, so one thing was that basically like people use sort of the kind of the perceptual loss in the kind of the training of the neural net. So that's kind of the sort of the standard way in kind of many sort of the techniques like learning some sort of the generative models. But when you typically say about the perceptual loss, I mean, these are basically things like just like taking some sort of the latent factors from the pre-trained models and just comparing these things, and just kind of assuming that this kind of pre-trained model or kind of like have some sort of the like learning some sort of the aspects about some real perceptual things, but we don't know whether the neural net really kind of learn any kind of perceptual things there. So do you think that like there will be some better ways that somehow we can really design some real kind of the perceptual kind of the loss kind of things, like the way that we can somehow really teach the neural net to learn some real the human perceptions in terms of like learning this kind of the right needs of the person?
Yeah. I think there are multiple things there. First of all, you can have two different papers that says we do perceptual loss, and then the result you get are completely different. Even though they're trying to solve the same thing. You can use two face recognition networks that extracts the identity, and on their papers they perform plus minus epsilon similarly on some data, but when you plug them into our avatar system you get completely different results, which is kind of interesting. So so you're right. So the way it's being defined is kind of like, and that requires a lot of experiments and engineering to see what kind of works. But at the same time, I think that there is probably more to it, and it's just like one aspect of it, right? I think the description of like what is perceptual, because maybe there are other dimensions that also matter. Yeah.
Actually, also about the kind of the data-driven kind of approach. The one thing that I just thought was that, because now I also I'm kind of interested in this kind of research, but I was not really working the real some like human body or human face kind of things. But I was curious whether there might be also some of the issues in terms of like collecting the data, like if you also somehow like have some supervisions about the human faces or the human bodies, which means that you are also collecting this kind of the human face images or the human body images, then I guess there might be some issues in terms of like some, I don't know, like some portrait the right kind of things, some privacy issues, whatever things, especially in the case that when you kind of collect all these things from the internet. So how do you basically handle this kind of the data issues in your research?
Yeah, so right now, this is a good point. So one of the big things we want to, so for example, for the body digitization stuff that we're doing, we want to basically avoid even using any real data. So we want to, if you have all CG, you're done, right? So so we're really looking into how how to build something internally that allows us to just use CG content for training, and those quality get better and better. And then some data that is enough for generating realistic images. That's sort of like, I think, a good approach for that, right? And sometimes if you just collect real photos of people, it's kind of biased, and so the great thing about if you have CG content to create them, you have control over how balanced it is. So in addition to privacy issues, the best thing is you even control that. So, and actually in this avatar synthesis work, we actually use a lot of StyleGAN generated training data. Yeah.
Oh, I see. That's kind of cool. And also, do you somehow also handle to be the diversity of this kind of the data, like having some like Black people, like white people? Or
yes. So, so for example, I mean, we use public data sets for training, but we also generate a lot of data that are not real people. So we use GANs basically to generate data, but then we also add things that allows us to specify what kind of ethnicity we want and what kind of thing to have a better variation. Yeah, so things like that.
Yeah, I also think like we are seeing like some research works of like creating some data using some like procedural models or some generative models. But the thing is that also these kind of generative models and the procedural models should be also kind of created from this kind of the multiple images. So it's kind of like the things that we might need to have some sort of the loop, like from this kind of model, we can produce some lots of the data, but from the data, actually, we can make some kind of the better models. So yeah, there might be sort of kind of a loop, and somehow we need to somehow inject more things in this loop to kind of like improve both kind of things. But yeah, I also kind of curious about the kind of the typical way that people handle this kind of like iterations of like developing these two things.
Right.
Yeah, that was also the questions. And the other thing might be is that I guess here the audience, many of the people in the audience might be also interested in the neural rendering, the nerve things. Like everybody is like talking about the kind of nerve. But I also kind of curious, like how you also kind of see like the sort of the future of this kind of neural rendering, as you also mentioned, like still the people are kind of using some sort of the classical approaches, like just defining the 3D assets with some sort of the meshes or the textures, whatever things, because like these are kind of the typical way that we are making some 3D content and also kind of like render these things into this some game or any kind of the graphics pipeline. But the nerve might be basically the new way, but this was kind of the very new sort of the way of like representing all the 3D kind of the virtual kind of things. So I guess it might basically like in this kind of take some time to basically that the nerve basically somehow replace some sort of the classical the engines, but also there might be also some issues, like not only for the rendering, but the time when you also kind of like try to edit some of the 3D contents or make some sort of some dynamic motions, whatever kind of things, there might be still some issues in the neural rendering kind of the technologies. So I was just curious, like how you kind of foresee like this kind of the techniques, how this would kind of like affect to some real sort of some industry sort of the products.
If you remember, maybe 10 years ago, something like 10 years ago, people got all excited with things that companies like Lytro created. They have basically camera arrays, and then people were interested in all kinds of things around light field capture and this and that. And the killer demo back then was you take a photo and you can basically do the focus thing. And then a couple of years later, Google released like an app, and then it's just using, I can't remember what they used, but then you can just like estimate roughly the depth from your image, and you say, oh, look, you can do the same thing. So I think, and then you have like different tech companies, like I think they're called Fuse or something, where you can rotate something and it does a little bit of stabilization, combine a little bit with multi-view stereo, and then you can create some interesting content. And I think it's going to be very similar with Nurse first. So there is actually a company, I think, called Luma.ai. And they're starting to explore, look, we can use, and probably it's using Nurse to create some new kinds of effects. So I think one thing that's kind of interesting these days is that startups will very quickly explore, a new tech and which kind of industry will kind of pick this up. And some I think might figure, and it might not even be what we think it is, right? So a good example is like Matterport, that company. So when they scan environments, back then I never have thought they would use for real estates, but now if you want to rent an apartment or Airbnb, you can see, oh, this is all Matterport. So people who are going to use that, maybe it's going to be used in movies. Maybe I don't think it will replace games that quickly, but it could. I think if you build a good system, it could replace these, in my opinion, boring 360 panorama views in VR, which is, I think, that it just looks, it's just like a 360 view. But if you have a content where you can actually move around and have that immersiveness, this could be a really great app, because the big advantage is that you don't need a content creator behind. Like, people can be the creator.
Yeah, that's really good. Actually, while also kind of waiting for some more questions, well, some other questions might also be is that one question would be like, basically, as kind of the researcher, very actively working on both the academia and also the industry. How do you, I mean, also not only for the NERF, but also like in general, like how do you feel like some sort of the research in the academia are kind of like, also affecting to some kind of the real products in the kind of the industry? Like, do you kind of like very actively kind of like adapt all the techniques that you develop like in the school, in the university, into your products? Like, I mean, how is the kind of the process that some kind of the techniques that were kind of born in the lab in the universities are kind of the adapted to some kind of the products in the in your company?
So I think it's probably generally true that in academia you would create like so your paper output basically shows that something new is possible. And whether it's the way to go is another question. And in industry, it always takes it typically takes more time so that whatever you build becomes even a product. And one thing that I found out is that many of the stuff that we develop in research, the results that you see in papers, sometimes they show that it's possible, right? So you get some super nice looking results, but then once you add other data, you're like, wow, it doesn't look that good. And it's normal, because you show a prototype, and but then making it really robust is an entirely different problem. So you need to make it work on every kind of person, every kind of situation. And it's a bit like computer vision in general before deep learning. Computer vision before, it's like, everyone knows now, it's like, how can people even do that? Like, it works at, face recognition is not even 60% or something. And now it's like 99.99999% accurate. But before, it was like 60% is already pretty good. And people would like, oh, of course you're wearing glasses. Of course it's not going to work. So things change, right? But on the other hand, I think one thing that is important is that I think, at least I've learned actually from doing the startup, is that we have to think a little bit the other way around, which is not like, I have a technology and how do I apply this to a new product? It's more like the other way around. It's like, what do people really want? And I give you an example. For example, for our Expo 2020 project, people, in that specific case, the art direction, our customer says, no, we want stylized. It has to match the style that we're creating. So the avatars that we're building match a very specific art style. And that it's very interesting too. It's not like a paper where when you do papers, the only thing that you care about is you're an epsilon better. I mean, it could be much bigger than epsilon. You have to be better than what's prior work, and you have to be different. In real worlds, you don't really care if you're different or not, and it doesn't matter if you're how new your idea is. It has to actually work, and it has to match. Not only has to work, it has to match what people really want. And but then, you know, if you come from a scientific background, you're interested. But it doesn't mean you only have to think like this. You can play both ways, because without the other, you can't really come up with new things that your customers haven't thought about.
Yeah. And also I feel like there might be some difference between like running the startup, like developing some just kind of new services, but like also the running the startup, like developing some new technologies. I think your case might be like really kind of be making sort of the like focusing on like developing some technology. So that would be kind of like adapted to some sort of the services at the end. But I guess there might be some sort of the kind of some differences, like just kind of like making some kind of the web service, just kind of like having some more, the customers there. But
I think for tech companies, like tech startups that have, I mean, there are different kinds of startups, right? So one startup is you already know what the killer app, or you already know what the killer app is, and you quickly demonstrate and you get massive amounts of users. For tech startups, you have an idea of like how people are going to do certain things in the future, and then you build your tech, and then you have to validate it, but maybe you have to improve the technology. And I feel that I mean, we were in the avatar space for a couple of years now, and many of our competitors that are working on 3D avatar, I mean, none of them have actually, you know, turned into $1 billion business yet. And some of the reasons is because the technology isn't there yet and isn't perfect. So that's why we're aggressively working on that. But also because, first of all, if you think about it, like 5 years ago, you didn't have all these deep learning things, right? So the technology wasn't there yet. So it's all very new. And also no one even mentioned, I mean, not many people mentioned the word metaverse as they are mentioning now. I mean, back then people mentioned the VR, and then it had a little low, and now everything is going up again. And no one talked about NFTs in the past, right? So people have a completely, so the economy is also working in parallel. So you have to adjust like what is going. Nobody knew about the pandemic, right? So after the pandemic, everyone wants to go completely virtual. Before it was, avatars are nice, but who needs it? And now it's like, why didn't we do avatars, right? So do you have avatar solutions? Because no one is going to our stores anymore, but we need a virtual assistant now on our website suddenly, right? So a lot of things change. But one thing that is true is that it is, I think that it's going to happen, right? So that people are going to use virtual avatars. But so it's always like things that change like this.
Yeah, I think now might be really kind of good time to really work on this kind of like virtual kind of avatars and virtual things, like given this kind of the pandemic situation and that kind of the big interest in the metaverse. Yeah, I think if there's no question, we can kind of wrap up. As kind of the last question, could you just kind of give any kind of the last comments for the students here who might be kind of interested in like doing some research in this field, or kind of any kind of opportunities, like in terms of like making this kind of the avatars and virtual scenes, and also maybe probably like just working the Pinscreen or like any.
Yes, we're hiring. So we have multiple positions. So whoever is interested in, I don't know, doing an internship or even working full time, we're hiring researchers, graphics engineers. Can be undergrad, can be graduates, can be PhD students. So we're hiring right now, and then feel free to shoot me an email, and then I can we can follow up. Yeah, cool. Yeah, thank you very much for giving the very nice talk for today. Thank you so much for having me. Thank you. So we are ending the Colloquium talk here. Thank you. Thank you. Okay, we have like kind of last question, but would it be possible to? Yeah, I see it right now. do you have any idea connecting nerve modeling and classical mesh modeling to do some physical simulation like hair waving? There must be a connection relation among voxels or volume info of nerves. Okay, so nerves are a great idea to model things like hair, because hair are complex to store. And then the question is, how do we connect nerve modeling and classical mesh modeling? Well, the idea of nerves is to not use any mesh at all. It's to represent everything implicitly. But there is an advantage if you have some understanding of the mesh, because maybe you want to be able to manipulate it. So, if you just, maybe not nerves particularly, but if you just look at neural rendering, I think there's all these work where people translate renderings of CG models into photorealistic scenes. So yeah, probably there's something in there where you can relate things, because if you can relate things, then you want to be able to control things. But I don't have a specific answer right now on that. Yeah,
I guess there is just kind of some new research, maybe sometime soon, about like some of making sort of the hybrid version of like having some more like
there is
explicit.
I think
Yeah.
there is. There's so many work on that, it's hard to even keep track.
Yeah, there's so many kind of things related to neural rendering. Yeah. Any more questions? I guess we can like wait for like 5 seconds. 10 seconds. Okay, if there's no more question, then we can end here. Okay, thank you.
Yep, thank you. Have a good day.
Yeah, bye.